Okay.
Okay, so it's a pleasure to have today Carlos Hoppen. He's really a person from applied mathematics, so no PDEs today. And so Carlos Hoppen is professor at Universidad Federal do Rio Grande do Sul. He did his PhD in combinatorics and optimization at the University of Waterloo. And so it's a pleasure to have you, Carlos. So you may start.
So thank you very much for the introduction. And actually, perhaps I'm really at the boundary between applied math and pure math, but what I have to say today is definitely applied math. So I'm happy to share this research with you. And it's about community detection in random geometric graphs. And I am a professor at Universidade Federal do Rio Grande do Sul, which is in Porto Alegre. And also, I'm currently the president of the Brazilian Society of Computational and Applied Mathematics, which is SBMAC. And not for long, I'm still there for a couple of months. And then my colleague Soledad Arona from FGV will be the next president. But so I'm going to talk about community detection in random geometric graphs. And my work includes joint work with Luis Emilio Alem, who is pictured here, and Konstantin Avrachenkov, who is like down here, and Hariprasad Manjunath, who is now at Chaitanya University in India, and he was a postdoc of Professor Avrachenkov at the time of this research, and Lucas Siebenberg, who is a student, now a PhD student of Emilio and I. And he actually did many of the slides in the sense that he has nice pictures and then I borrowed them from him. So I'm very thankful to Lucas for the presentation. And I'll give some background, some motivation about the problem. I'll talk about spectral clustering and then give some results. And that's the topic of the work about community detection in the soft geometric block model. And I went with some final remarks. So what's the problem? So I'm interested in data clustering. And the idea is that I'm partitioning a data set into groups of objects. And the idea is that objects that are similar should belong together and objects that are different should be in different groups, right? So that's the general aim. And so Jane, who is an expert in the area, he said that cluster analysis is the formal study of methods and algorithms for grouping or clustering objects according to measured or perceived intrinsic characteristics or similarity. And of course, when we read that, it's for a mathematician, it doesn't seem to be a very well-defined problem. It's in the sense that what could be like these perceived intrinsic characteristics. And so one of the things is that clustering depends on context. And this is an example that from Lucas. So Lucas really likes, I'll call it football. And and then he has this example where he has like players from different countries and different generations. And if we look at these players and we decide we have to split them into clusters. One idea would be to identify the countries, because which country does each player play for, and that would be a way reasonable. Maybe the generation would also be a way of looking at it, because those two players played in the 70s and those are playing, or some of them right now, some of them are retired, but they're more recent. Or like in Lucas's point of view, and that's a joke that only people from Brazil and probably from southern Brazil understand. Those two players played for Lucas's team in his heart. So they are in one group and the others didn't. So it could be like that as well. So like it's a joke, but what I want to say is that in general, like if we only say we want to cluster, it's hard to say exactly what we want, right? And so for mathematicians, the first thing would be to try to have a problem that is well stated. And so suppose I want to work with data clustering in a metric space. So let's imagine that that's like a Euclidean space. I have some points. And my idea will be to cluster these data points into two groups. And maybe it makes sense to think that the two groups, like, of course, on the left, that's a way I could separate the points into two groups. But on the right, it's probably more natural that I'll have the group on the top right and bottom left, and those would be the two groups, right? So tighter clusters look more natural in these metric spaces. And one way of measuring this would be to measure the center or the centroid of each of the groups. And I can construct that if I have, say, a vector space. And then I measure the distance from the points to the centroids. And then on the left, the distances are large, and on the right, they are smaller. So maybe on the right, that makes more sense. And so that would be maybe like a very natural formalization of the problem, where I start with a data set in a metric space, and I have a number of k, that is the number of clusters that I want, so the number of groups. And the metric in the metric space measures the distance between the elements. And then what I want to do is I want to measure the distance between elements that are in the same group. And then I sum, and just because okay, there is a technical reason to do that, but it doesn't really make a big difference for what I'm telling you right now. Like, we just take this and we normalize by the sizes of the groups. And then we sum, and if this is small, right, it would mean that the f of p would be small, and then the distances in the group will be small. And so the elements should be clustered together. So one possible way of stating the problem is I want to find the partition that minimizes this function f of p. And so that would be a way of formalizing. And I just wanted to call your attention to the fact that the number of classes has to be part of the input, because if I put more classes, the value can only go down, right? So it's kind of course, it would be like the best solution would be if each point would be its own cluster, but then that's not the aim, right? The aim is to have a small number of clusters, so we give it as part of the input. And there is a natural way of solving this problem. And I'm just going to, maybe I'm not going to read the entire thing because the idea is simple. I'll start with a partition that could be very bad. I don't know what it is. And then at each step, I will compute centroids, which are the centers of the clusters. And then I will create a new partition where each point goes to the centroid that is closest to it. So anyway, so an example like this, suppose I have these three sets, and then maybe the natural thing would be to have one here, and the other here. And I'm aiming for 3 clusters. So I could maybe start by selecting 3 points randomly. So suppose I did that. So I chose that one and that one and that one. I chose them randomly. And now I assign each point to the centroid that is closest to it. So I would get the partition on the left. So every point was assigned to the point that was closest to it at the beginning. And then, of course, now I can update the centers, because now I have like new points. So the center from the red went here, and these others move a lot, right? So the center from the green goes to the middle, and the blue the same. And then I do the same. I again put every point to the closest one, and I iterate in this way until I stop. When do I stop? When I iterate and I get the same solution that I had before. And in this case, I recovered exactly like the partition I had at the beginning. And this procedure is known as k-means clustering. It's quite old. So here, even I'm giving these references, but perhaps those references are more related to the first time people were actually writing about those things than actually having new ideas, because this kind of algorithm was very natural. But k-means ends after a finite number of steps, so one can prove that. And the partition produced by k-means, they are convex in the sense they're not convex sets, they're just points, right? But if we take the convex hulls, they don't intersect except possibly at the boundary. So that's would be a natural thing about this procedure. One comment is that if it can stop at a local minimum. So it's not true that this is a simple algorithm will actually solve the problem I had mentioned before. It's just a procedure that can find a local optimum. And the output then may depend on the initial partition. And there is a different strategy for the problem, which I mentioned here. It will be useful for my talk, that there is an efficient algorithm for finding an approximate solution, which is an approximation of the optimal value. So a 1 plus epsilon approximation can be achieved in polynomial time. Okay, so just to give an example, let's suppose we have this image here, and this image has a lot of pixels and it has a lot of colors, and maybe it requires a lot of space for it to be stored in some machine. And so maybe I would like to have fewer colors, but still recognize what's going on. And how could I look at this? So each pixel in the picture may be associated with a color in some system. Here I'm supposing red, green, blue. And that's a vector in 01 cubed. And I could think, okay, maybe I'll look at the vector as the color, right? So of course, now I have points in a vector space, and those are, each point is embedded to the point that corresponds to its color. And I could use the algorithm I mentioned before to try to cluster. And then I need to tell how many colors I want. And just to give you an idea, suppose I wanted 2 colors, that's the picture I would get. And 3 colors, there is something else that appears, and then 4 colors, and then 8 colors. And 8 colors is not so bad, right? I mean, of course, it's much worse than the original picture, but you can imagine that if we had like 200 colors, it would be good, at least for me. Like maybe for people who have a more artistic view, they would see that there are colors lacking, but for me, it would be fine to have maybe even less than that. It would already be fine. And of course, the centroids in this application, the centroids not only tell you which groups are together, but they also tell you which color you should use, because the color would be a mean of the colors of all the points that I'm putting in that area. So it selects and it gives an idea of which color you should attribute to each point. Anyway, so that's an easy application, and it works, right? K-means works for that. But suppose now I have a more complex data set. So now I have a data set, it's embedded in a metric space, but now the data set is not something about points being closer together, but maybe I can see something in the picture that show me some structure. And here the idea is that I would have like 2 circles, right? So that's what I'm seeing at this moment. And I would like my algorithm to identify that I have my data points are essentially in 2 circles. If I apply k-means, I'll get something like this. And there is no way I could get anything better because things have to be centroids, right? So I'm just looking for closeness. And so there is no way I could find one cluster here and the other cluster outside. So there is no hope to apply that algorithm and get anything that is better than this. However, I would like to find that one. And spectral clustering appears in this way. So here, that's a brief description. I have a data set, and my data set has a number of points. And I have a given number of clusters, which is my aim. I want to partition in that number of clusters. And I need to define something that is a similarity matrix. And the similarity matrix will tell if my points are close together. So in the first application I mentioned, similarity would be completely related with distance. But now perhaps in this other case, I could try to argue similarity in some different way. And what we do in spectral clustering is that we compute orthogonal eigenvectors, because this matrix will be symmetric in essentially all the applications. And so we have orthogonal eigenvectors and associated with a certain number of eigenvalues of our matrix. And we use the eigenvector. So the matrix I have here is a matrix that is n by k. So n is the number of points and k is the number of eigenvectors I choose. And for each point, I now see a vector with k coordinates. So I can associate each point with a point in the space with, in our case, say, or so right. So that's what I would get. And just to mention, so the similarity matrix very often is a Gaussian function associated with some distance in a metric space, but could be something else. And the matrix associated with S is very often a kind of matrix that appears in spectral graph theory. And I'm not going to define those things in detail, but there is something called the Laplacian, and then a normalized version, which is the normalized Laplacian. And there is another one that is adjacency. And what I'm mentioning here is that typically for Laplacian type matrices, the eigenvalues that are useful for this are the smallest eigenvalues, so the k smallest. And for the adjacency, typically it's the k largest, right? So that's how it normally works. So you choose the matrix and you compute. So just to give you an idea, if we use this original algorithm by Ing, Jordan, and Weiss, and this algorithm would do the following. So it would have two classes. It would compute the two eigenvectors. And so each point would go to R2, and this depicts the embedding, right? So each point, the red point would end up here when I use this embedding, and the blue points would end up here. And now it's clear that if I try to use spectral k-means, a geometric type of clustering, right? The one I mentioned before, I would be able to separate the red from the blue. It's clear that that would happen. And even here, a step that those algorithms normally use is to just renormalize so that they have norm 1, and because otherwise the vectors could have a very small norm and then they kind of are clustered, they're too close to 0. But if we renormalize, we can see that the two sets get far away from each other and they allow us to recover this structure. And so normally when we have some artificial set like this one, where we construct things, typically spectral clustering will work. And if we look at how things are computed, it kind of ends in an example a little bit like this, right? So that's an example. And so they have those spectral clustering algorithms have proved to be successful in in identifying clusterings for synthetic and for real data sets. And there are rigorous results about them. Oh, sorry, I should be here. So one is by Spielman and Tang from 2007. And they showed that spectral partitioning methods based on eigenvector associated with the algebraic connectivity, that comes from the Laplacian. It works well for bounded degree planar graphs and finite element meshes. And then von Luxburg, who is also like a famous researcher in the area, and her co-authors obtained results about the consistency of spectral clustering. So under some mild assumptions, they have shown that clusterings constructed by Laplacian-based spectral clustering algorithms converge almost surely to a limit clustering of the entire data space. So if I take larger and larger data sets with the same overall structure, I get the same type of results in the limit. And there are results by Lee, Garan, and Trevisan, who provided theoretical justification for algorithms that use eigenspaces associated with the bottom k eigenvalues to embed data points in RK. And so they don't quite use k-means, they use other geometric-based algorithm, but they can show some guarantees about the solution. And for people who have heard of property testing, there are also results about recognizing cluster structure using property testing. But so those are some of the results. There are many more results, but not that many, in the sense that we don't have rigorous guarantees about the solutions that we get. And one of the hard things is that typically, if I wanted to get a result, K should be part of the input. And it's kind of clear that sometimes for my data set, some value of K will be very bad for that data set. It clearly doesn't have, say, 7 clusters. So trying to prove things that are very general for any data set, for any number of clusters, doesn't seem to be feasible or even reasonable. So one idea where it makes more, maybe it's easier to analyze and where there are results, is community detection in random graphs. And so when we talk about random graphs, maybe the first idea would be to use Erdős-Renyi random graphs. And so that's GNP. I have n vertices, and each pair of vertices is connected with an edge that comes with probability p. So the vertices are really randomly connected to other vertices. But then those graphs have absolutely no community structure. Every vertex is as likely to connect to any other vertex, so it doesn't make sense. But the very natural random model in which spectral clustering algorithms have been considered is the stochastic block model. And it's similar to GNP, but we choose a cluster, right? So we start with a set of clusters, so with K sets, and we put probabilities between vertices according to the clusters that they lie in. So for instance, I could put a probability for points that lie in here and some probability in here, and then a probability for points from here to here, and so on. And then we can adjust the probabilities so that I'm more likely to have neighbors inside than outside. And that's so Holland, Lasky, and Leinhardt proposed the method in this way. So we generate a graph with vertex set v1, vn, and we make it homogeneous if we use one probability for edges inside the class and another for vertices that lie in different classes, right? So it's a simplified version of the general version I mentioned before. And in this case, we could have something like this. So here I have a stochastic block model where I have 3 clusters of size 30. And the probabilities are 60% to be connected to a vertex in its own cluster, and 5% to be connected to one from a different cluster. And in this case, like we really see that it's much, much more dense here than between vertices from different parts. And if we look at the matrix, it's really clear that here I will have like some dense parts and some points from different classes, but the dense points are clear. So just to make sure, like the blacks mean that I have edges and the whites mean I don't have edges, right? And we can see naturally that we have 3 clusters here. And how do we measure then the quality of an algorithm? So suppose I have n vertices and an adversary fixed the partition and generated a graph according to the model. And let's suppose I have this other partition that was generated by spectral clustering or by another method, but I have an estimator. So I compute the Hamming distance between the two, which means of course, I need to use permutations, but I want to find the number of changes I would have to make in one of the partitions to get the other. So the number of points where they're different. And that's what we call the loss. And this is just a loss that a version where I divide by n so that the value is between 0 and 1. And there is a result by Ley and Rinaldo where they consider a stochastic block models where you have P in being like a constant times some rho n and P out a smaller constant times rho n. And we have the average degree. And the authors can show asymptotically almost surely that the loss that we have will be at most C times 1 divided by the average degree. And typically, if I'm thinking about large graphs and the vertices would have many neighbors, then the average degree would be large, or if n goes to infinity, they would grow with n and go to infinity. And so this would go to 0, right? So that would be a result showing that it works for the stochastic block model. And they proved the consistency of spectral clustering applied to the adjacency matrix of the stochastic block model. And here it doesn't have to be classes of the same size, but they need some conditions where the classes are not too small and where the maximum degree is at least something that grows logarithmically. So that's the hypothesis they use. And there are results by Koya-Oglan and by Mosso, Niemann, and Sly that show that if the maximum degree is bounded, which means it doesn't go to infinity when n goes to infinity, then communities can only be recovered up to a constant fraction. There is no hope that the algorithm would work. So there are results about the stochastic block model. But the stochastic block model is perhaps too simple, right? I have the sets there, and I really decided which ones are closer together. And in the group of people who are closest together, they are all more likely to know each other than, say, know someone from another group, which is not maybe a reasonable assumption in any application. So another type of community detection would be like this. So this is an example. Suppose that I look at the students, and they could be in elementary schools or high school. So here, like we have in Portuguese, like fundamental, which is elementary school, médio, high school. And suppose that we have a graph where we can identify for each student who are their friends. So other kids that they know that go to school. So what happens? Now we look at the graph and we can see for each person who their friends are, but we cannot know, we are not told which students belong to each group. And the question would be, can we find out which students are elementary students and which students are high school students just by looking at their friendships, right? And it makes sense that high school students will be more likely to know other high school students, and elementary school students will be more likely to know other elementary school students. But it's not true that they're more likely to know elementary school children from China. And even like that, in China, probably elementary school children are more likely to know other elementary school children than high school students. Anyway, so that's maybe the intuition about it. And a way of trying to simulate this type of thing using a random model would be to consider a set of points divided into a set of communities. But the random graph is not generated like in the stochastic block model. We add some geometric perspective to it. So we embed the points in a space. And here I'm talking about the torus, but that's just because it makes computations easier. But the idea in general would be to take the points and embed it into a metric space. And when I compute the probability of putting an edge, the probability depends on whether they belong to the same community or not, but it also depends on their distance in the metric space, right? So it gets this other geometric component. And why do we use the torus? So here, the one-dimensional cube and the one-dimensional torus, the two-dimensional cube and two-dimensional torus. And what's the difference? If I choose points randomly on the cube, depending on where they lie, their neighborhoods have different sizes. And so if I know something about the friendships, I would deduce something about the position where the points are located because of how the space works. And like in two-dimensional too, like if I take a point here, maybe the neighborhood will be something like this, but closer to the border, the same neighborhood would be smaller. And on the torus, that doesn't happen, right? So, and also on the torus, we can just use a natural generalization of the Lebesgue measure, right? We can interpret this as a torus where this side and this side are the same, and that side and the other one are the same. So so that's why I'm talking about the torus. And two special cases of this model would be the case where both are constants. So the f in and f out are constant functions, and that would be just the stochastic block model. I would have some probability for inside and one for outside. And another one would be the geometric block model. And geometric block model is deterministic once I know where the points are. So I have two radii, r in and r out. And the probability is 1 if the points lie at distance at most r in and they are in the same class. And it's 0 if their distance is larger, right? So here, the only part of the graph that would be random would be embedding the points in the space. Once I have the points in the space, I know which ones are connected to each other. Of course, if I start with the communities, right? So because the probability, the radii depend on the community. Okay, so here that's an example. I understand that it's very hard to see what's here on the left, but that's a torus of a dimension, like just a circle, right? So the dimension 1. And we wanted 3 clusters. And so, and there were 400 points. No, 4 clusters and 400 points. So each cluster had 100 points. And the points were chosen randomly around the circle. They were embedded. And then here, like, there are more yellow together. And anyway, but of course, it's hard to see. And there are radii are in and are out. And the adjacency matrix, when we chose this graph, would be just like this. And here it's just geometric. So if they're close together, they are automatically connected to each other. And here we also see like that the groups, vertices from the same communities are more likely to be together. We can see the structure, but it's much less clear in the sense that here we also have many other connections. And just to see that the problem is not completely trivial, like here I can see the structure because I ordered the vertices according to their clusters. But if they were ordered in, say, a random way, it would be much harder to see what's going on with, right? So that it would be hard to put the matrix in this form, right? So anyway, if perhaps, let me just say what I wanted to show here. If I have a problem like this, that's the original partition. And if I try to use the traditional spectral clustering, the one I mentioned before, it wouldn't work. It would still find, like the colors you can see, they don't quite match. It would still use a lot of the distance as a way of putting the points together. And the one I'm going to talk about is this other method that we'll describe here. And okay, so let's come back to the problem. The problem is community detection in the soft geometric block model. I'm given a final graph that, say, my opponent created, and our team has to identify the K communities that were used to build the graph in the way that was described before. And the important parameters of the model are the expected intra-community and inter-community edge density. So that's the expected edge density within for vertices with other vertices of their own community, and those are for the vertices from the other communities. And then, of course, by the way things are defined, these are computed by integrals. And what does the algorithm do? So I start with an n-vertex graph and a number of clusters. And I have, according to the model, an average intra-cluster density mu in and another average extra-cluster density mu out. And those are given. They are a parameter of the model. And I need to find the partition of the vertex sets. So what I do is I compute again the spectrum of a graph of the in this case the adjacency matrix, but with other matrices it works as well. I mean, if we run the algorithm, it works as well, but like the proof doesn't work for other matrices. Our proof is for the adjacency matrix. And then what we have to do is not to use the largest eigenvalues or the smallest eigenvalues. We have to find a specific set of eigenvalues that are closest to a certain number. And the number is this one. Is the distance between mu in and mu out divided by the number of clusters I want times n. So that's the number that we got. And then we compute the eigenvectors associated with those eigenvalues that are closest to the value, and then we apply the same thing. So that's the first time actually that we, or this type of work, and I'm going to say not the first time my contribution, but Avrachenkov, which is one of the co-authors, had worked on that in the specific case of two communities. And that was essentially the first time where you would take an eigenvalue that is kind of in the middle of the spectrum, and that eigenvalue would be used for clustering. Normally it was top eigenvalues or bottom eigenvalues that were used. And so I leave just a reference here for someone who is watching that you can find the details in this archive version of the paper, so multi-community spectral clustering for geometric graphs. Okay, so our result is kind of technical, and I probably am just going to give some general ideas, but just to understand what's going on. So I have k fixed, so I have a number of classes. N is large, so I imagine that k, the number of classes is fixed, but the number of points is very large. And in our work, we consider the easier situations where we have k communities and all of them have size n over k, so they are equally sized. And then we have f defined as before, like we have the torus, it's defined on the distance. And f has one component for points that lie in the same cluster and another one for points that lie in different communities. And we suppose that mu in is greater than mu out, that is greater than 0. Of course, this kind of, I mean, if we had mu in less than mu out, it would work, but it doesn't really make so much sense because we would imagine that points lie in the same community if they have more affinity to each other. So it's natural to consider mu in greater than mu out. And it's also clear that if in my model mu in and mu out were the same, I would not be able to see the difference, right? Because a point would be equally likely to know someone from its community, so it's not really a community. And in addition to those very natural things, we need f, mu in, and mu out to satisfy some technical conditions that we use in the proof. And those technical conditions are given in terms of the coefficients of a Fourier series. And of course, like why? Because the Fourier series will have has to do with the spectrum, right, of the operator, and then that's why it works. And once we have that, those hypotheses, which are very vague in what I said, we can prove the following about the model. So the k minus 1 eigenvalues of A, and that includes multiplicity, that are closest to the value. This is the value that I said the algorithm works with. I'm looking for those that are the eigenvalues that are closest to this in the algorithm. One can prove that those eigenvalues, they are far from any other eigenvalue of A. So those eigenvalues are kind of isolated from the other eigenvalues, which means that an algorithm could actually identify them, because you can imagine that if we only run things numerically and n is say 10,000, then we would have like 10,000 eigenvalues. And looking at the ones that are closest could be hard because many of them could be close to a certain value and we only work with approximations. So this result shows that we do have k minus 1 eigenvalues that are isolated from the others. Then we consider the matrix so that the rows of the matrix are the points and the columns are the eigenvectors, as I did before. And then what we can show is that if we apply k-means clustering to the embedding that we produce, then asymptotically, almost surely, the error that we get, so that's the actual clustering, and that would be our estimate, and the distance would be at most log n. And if we go to a third step, where we use these clusters that we found on B, and we perturb them by asking each point, do you have more neighbors in your own class or in some other class? If the answer is some other class, we just move the point to another class. So if we do this perturbation, then asymptotically, almost surely we recover perfectly, right? Perhaps C looks more surprising first, but it's not. Once we have B, because of the structure of how the graph is created, once we have a pretty good approximation, then it's natural that we can find the structure just using the neighbors, because then it becomes almost SPM. So C, I like to mention it because it shows that the algorithm gives the solution almost surely. But on the other hand, it's not surprising. The surprising part is B, that we can really recover a solution that is so good that we can use it then to recover the full solution. So that's the result. And let me just give you an example. So the setup will again be a one-dimensional geometric block model. So that's the example I gave you before, where we had 1,000 points in 4 communities. No, sorry, that's larger. The one was 400 points. So this one has 1,000 points in 4 communities. So each community has 250 vertices. And then we compute the random graph. And again, it's the random geometric graph. Once the positions are set, we only have the radii that define if the distance is smaller than something, there is an edge, otherwise there isn't. And with those parameters, this value lambda star, which is this average here, would be 160. So if we compute the eigenvalues, they will be ranked. And the eigenvalues that are closest to 160, the 4 eigenvalues are, oh, sorry, 4 communities, I need 3 eigenvalues. The 3 eigenvalues are those. So I just put lambda 3 and lambda 7 to see that there are some gaps. Lambda 3 was 181, and then we have those 3 eigenvalues, which are 163, 162, 160, and then the next one is lambda 7, which is 97. So there are like kind of jumps that we can see, and the theorem would say that those 3 eigenvalues exist here. Okay, right. And when we apply the embedding using those eigenvectors, we would get that. And here we can see, so that's in 3D, right? And then we can see, because we have 3 eigenvectors, and then we can see that the sets are kind of far from each other. At least it's reasonable that if I apply the geometric model, I would be able to separate the different clusters from each other. And if I had used the largest eigenvalues, which would be the natural thing for adjacency matrix, or I mean, if we try to replicate the usual spectral algorithm, I would get sets like this. And so we can kind of see that those 2 sets would be able to be separated from the other 2, but there would be points from the 2 sets that would be confused if I try to separate, say, purple from blue or yellow from green, right? So that would be a problem. And so what are the main ingredients of the proof? So we should understand the spectrum of Gn as n grows. We want to show that the spectrum of Gn asymptotically almost surely has k-1 eigenvalues that are well separated from the remainder of the spectrum. And then finally, we need to show that the solution of k-means, actually, we don't use k-means, we use the 1 plus epsilon approximation because that's the one we have control over, the other one not really, essentially gives the right classes. So, or let me be clear, in an application, we would use k-means because it works. But if we want to prove something about it, k-means is very unstable because it depends on the starting points, and then we would use the approximation that is a well analyzed algorithm. Anyway, so that would be the 3 steps. And the first thing is understanding the spectrum. And for this, we define a sequence of measures. It sounds like measure, but it's just because I want to take limits, because really those are discrete measures in the sense that I only keep the eigenvalues of the graphs and I normalize them so that the thing is in a bounded set. So the eigenvalue of a graph from the adjacency matrix is always at most n and at least minus n. So those points will lie between -1 and 1. So we define this sequence of measures. And we have this other measure here. And this measure is given from the Fourier series, right? So I'm not giving any details, but there is you can have a Fourier series associated with the function f, with f in and with f out. And using those, we can define this measure that is the mu here. And then what we show is that those measures which represent the spectrum, they converge to this measure here when n goes to infinity. And then for the convergence is a weak convergence. And of course, because everything is random, like it doesn't always converge, but we can show that almost surely it converges in this weak sense. And to prove that, that's where we need technical conditions on the Fourier series to have these results. And then concentration is obtained by computing moments, and Talagrand's inequality, that's for people in statistics or in probability, that's a well-known inequality for showing that we have the points are clustered together, right? Anyway, then okay, that's just a Fourier series. I'm also almost at my time, so I'll just skip. That's just the definition of the Fourier series and the Fourier coefficients. And those are the technical conditions. So the Fourier series should converge to the points of the functions close to 0. And there should be some differences between some of the Fourier coefficients and the mu in and mu out. Anyway, so those are technical conditions. They're not necessary, but they're used in the proof. So it's not that we can prove that unless this works, the algorithm works. It can work in other situations as well, but that's how when we can prove it. And then the second part is to show that that there are well-separated eigenvalues. And so the result is like this. You get there is an epsilon such that for any theta that is tau, sorry, for any tau between 0 and epsilon, we get the following. We get k-1 eigenvalues that are in this interval. So, and the interval is measured by this tau. And all the other eigenvalues are at a distance at least n times epsilon from the original, right? So that's the type of result that we get, isolating these k-1 eigenvalues.
Carlos,
And
can you try to finish, because there's another speaker after you?
Sure. I'm there. I'll finish. I just finished those two, and then it's good. So I'm not going to explain why, but there is a final algorithm, and maybe just mentioning that there is a theorem known as Davis-Kahan algorithm, a theorem that is used in statistics, and this theorem was the main tool for us to show that when we use k-means, or like the approximation for k-means, we can actually recover the original communities, because of course yeah, I mean that's maybe the hardest part, and the part that we needed to work on, and that's the thing that made the case general k much harder than k equals to 2, because for k equals to 2 the last step was not necessary. Anyway, so so maybe just to say some next steps, my method, like this case, was homogeneous, right? So we could have inhomogeneity in terms of the different clusters. We could have some imbalance between the classes. This case works for dense situations. Say a vertex would be likely to have many neighbors, but sparse situations are more complicated. So that's the next step. And also to consider other embeddings, say and when I mean other embeddings, maybe different probability spaces, different metric spaces where we could use different geometries. So yeah, so that's what I wanted to share with you. And thank you very much for your invitation and for letting me present this work. Thank you.
Thank you very much, Carlos. I'm sorry for interrupting you.
No problem.
Sometimes.
Thank you for interrupting me. Otherwise, who knows?
Thank you very much. So now the audio is open, and if somebody wants to ask a question for our speaker,
Okay.
So, okay, I think it's very interesting, and I have like several questions, but the one I think is does this is related to machine learning, because I think that you can teach some algorithm to classify some kind of information, no?
Yeah, so that's the clustering is, say, one of the basic problems that is used in machine learning and artificial intelligence. So it would be one of the steps, because normally it would be kind of a pre-processing step where you start with a lot of data, and the first thing you want to say is you don't have that much. You actually have some types of data, and then you can reduce the size of the problem. So very often clustering would be this pre-processing step for machine learning. So yeah.
Okay, thank you very much. I don't know if somebody else wants to have a question. I don't see anybody. Well,
that's fine.
Thank you very much, Carlos. That was a great talk. Thank you.
Thank you very much.
Thank you, Carlos. Thanks.
Bye.